So this is the 2011 AP Chem Free Response question, Form B, for question number 2. It says an 8.55 mole sample of methanol is placed in a 15.0 liter evacuated rigid tank and heated to 327 degrees Celsius. And at that temperature, methanol is vaporized and it decomposes to form carbon monoxide gas and hydrogen gas. And it's shown by the equation below. The reaction mixture contains 6.30 moles of CO at equilibrium at 327 degrees Celsius, and it's asking us to calculate the number of moles of H2 in the tank. So we know that there's 6.30 moles of CO being produced at equilibrium. And so that means that for every 1 mole of CO, I have to also produce 2 moles of H2. So they gave us 6.30 moles of CO, so that means I multiply my answer by 2 to get my moles H2. So as seen in this little equation set up here, 6.30 moles, and I multiply by 2 moles of H2 over 1 mole of CO, and I get 12.6 moles of H2. So for II, calculate the number of grams of CH3OH remaining in the tank. So we have 8.55 moles originally given by that part in the question. Now, we know that CH3OH is in a 1-to-1 mole ratio with CO because of the equation up here. Now, if I had 6.30 moles of CO being produced, then that means 6.30 moles of CH3OH had to be decomposed in order to form 6.30 moles of CO. So, knowing this, we originally had 8.55 moles, and I subtract it by how much decomposed, which is 6.30 moles, and we get how many moles are left in the container, which is 2.25 moles. Now, if we have our moles, it's asking us to calculate the number of grams. So we multiply this by our molar mass, and we get 72.1 grams. Now for AIII, it's asking us to calculate the mole fraction of H2 in the tank. So to calculate the mole fraction of H2, we have to get the moles of H2 and divide it by the total moles to get our mole fraction. So we know we have 12.6 moles of H2 because of AI, which is given here. Now our total moles is equal to all the moles of all the molecules added together. So we know we have 6.30 moles of CO because it was given to us right here. We know that we have 2.25 moles of CH3OH, given in part AII, which is here. And then we also have 12.6 moles of H2, which is given in this part, AI. Now, when we add all of these together, we get a total moles of 21.15 moles. And now, although this is 3 significant figures, 3 significant figures, 3 significant figures, and this is 4. The reason why this one is 4 is because when you're adding numbers, you don't necessarily care too much about significant figures, and you're more worried about decimal places. So for example, if you had 6.01 plus 6.0, although this is 3 and this is 2, you'll leave it as 12.01 because this is how accurate it's supposed to be to the 0.01. So you just add it and you leave it together. Multiplying, on the other hand, and dividing, on the other hand, is a different story. And then the mole fraction would be total moles, which is 21.15, and then we have 12.6 moles of H2, and this is going to be our mole fraction. Now, for part AIV, saying calculate the total pressure and ATM in the tank at 327 degrees Celsius. So for this one, we use the equation Pivnert, and we know our volume because it was given to us, 15.0 liters. We know our total moles because we just solved for it here. Yep, 21.15. And then we know our R, which is just a gas constant. And then we know our temperature, which is 327 degrees Celsius. But we have to convert that to Kelvin, so we add 273. Then we isolate P, and then we get our answer, which is 69.4 atm. Now for part BI, saying consider the three gases in the tank at 327 degrees Celsius. We have CH3OH, CO, and H2. So how do the average kinetic energies of the molecules of the gases compare? And explain. So because all the gases are at the same temperature, the average kinetic energies of the molecules are also the same. So let's take, for example, we have two containers of the same gas, but just at different temperatures. Gas on the right has more energy because as I increase my temperature, my energy also increases. And so if I had the temperature being the same for both containers, they would have the same energy. So therefore, to answer BI, if I had same temperature, then that means same kinetic energy. And so for BII, it's asking which gas has the highest average molecular speed and explain. So in BI, the one just before, in this one, we explain that kinetic energy is the same for every single molecule that we have. So if Ke is the same for all the gases, then that means that each part of this equation has to be equal to the same number of Ke. So let's just say, for example, Ke equals 4. So if Ke equals 4 and I had a big mass of 3, then that means my velocity had to be small in order to compensate. Actually, this is an error right here. This would actually be 1.15 squared. And so if I had a big mass, then my velocity has to be small in order to compensate. And vice versa, if I had a small mass, then I would need a big velocity. So by this idea, then if they're asking for which one has the highest average molecular speed, it's talking about which one has the biggest velocity. And if we know that a big velocity means a small mass, and that means we have to find which one of these three molecules has the smallest mass in order to find which one has the biggest velocity. So, looking at these three molecules, it's really apparent that H2 is the smallest in mass because hydrogen weighs less than all of these. And so that's why we know H2 is our smallest, because it has the biggest velocity, and therefore it means it's the fastest. Now for C, the tank is cooled to 25 degrees Celsius, which is well below boiling point of methanol. It is found that small amounts of H2 and CO gas have dissolved in the liquid CH3OH. Which of the two gases would you expect to be more soluble in methanol at 25 degrees Celsius? So, to understand solubility, some common things to note is that polar molecules dissolve better in polar solvents, while non-polar molecules dissolve better in non-polar solvents. So, to answer this question in part C, we need to know which one would dissolve better in CH3OH. So, CH3OH is a polar molecule. So, we know that H2 is non-polar, and it only has weak London dispersion forces. CO, on the other hand, is a polar molecule due to the difference in electronegativity between the C and the O. We know that CO also has greater London dispersion forces because it has more electrons than H2. And so by knowing that CH3OH is a polar molecule, then we also know that CO is able to form dipole-dipole interactions with the liquid CH3OH because they are both polar. Now, the nonpolar H2 isn't able to form these dipole-dipole because it's nonpolar and it has very weak LDFs. And so that's it for 2011, Form B.